Today, movies arrive on our screens like magic. We tap a button and invisible data streams down from a distant server. But a few decades ago, home cinema required serious physical hardware. A heavy machine sat waiting for you to physically feed it a movie. Look at this object, a standard VHS cassette. There's no microchip inside, no hard drive, no solid-state memory, just a bulky plastic shell, a blank white label, and two distinct spools behind clear windows. And if you pry that shell open and pull out the actual media, you won't find tiny frames of film. You'll find this, a continuous dark ribbon of rust-coated plastic. It is completely featureless to the human eye, yet somehow this featureless ribbon held massive 2-hour cinematic experiences, complete with color, music, and dialogue. How did engineers manage to fit an entire movie onto such a simple strip of plastic? The basic mechanism relies on magnetic recording. A television camera converts light and sound into electrical signals, and those signals are written as magnetic patterns directly onto the tape. That process works for sound, but video data is a different beast. Moving pictures require exponentially more information than a simple audio track. If you tried to record video the same way an audio cassette does, by pulling the tape in a straight line past a stationary recording head, you'd run into a wall of physics. To capture all that dense visual data, the tape would have to move past a head at breakneck speeds. The physical consequence of that speed is sheer volume. To hold a full 2-hour movie at that velocity, you'd need miles and miles of tape. A single cassette would be larger than the television itself. To make a compact home cassette possible, engineers couldn't just improve the tape. They had to abandon traditional linear recording and invent a new mechanical solution. The video cassette recorder handled that physical labor. With its heavy buttons, metallic chassis, and intricate mechanisms, the VCR operated as a complex piece of active industrial machinery. The engineers' workaround to the linear speed limit was counterintuitive. If the tape couldn't move fast enough to capture the data, they would move the reader instead. When you push a cassette inside, a mechanical carriage physically pulls the tape out of its shell and wraps it around this specific component, the video head drum. This rapidly spinning metal cylinder decoupled the speed of the tape from the machine's ability to read massive amounts of information. The engineering term for this breakthrough is helical scanning. The metal drum is intentionally tilted. While the tape creeps forward, the drum spins rapidly against it. Because of this tilt, the heads paint data in diagonal tracks. Like slanted stripes on a narrow road, this drastically increases the total readable length. By packing dense data diagonally, engineers forced hours of video information onto a slow-moving, narrow strip of plastic. The diagonal tracks held the video, but the top and bottom edges of the tape were reserved for linear data. These edge tracks carried the audio and a synchronization signal to keep the entire machine timed correctly. That timing required microscopic precision. As you watched a film, motors and control systems inside the VCR were constantly adjusting in real time, fighting to keep the spinning drum aligned with those invisible tracks. The moment that tracking alignment drifted by even a fraction of a millimeter, the picture on your TV screen would instantly warp and degrade into a mess of harsh analog noise. Reading this data required extreme physical coordination. Pressing play initiated a highly synchronized mechanical ballet happening deep inside a black box. When JDC developed the VHS format, they specifically targeted a 2-hour recording capacity. They wanted an entire feature film to fit onto a single cassette, an ambition made possible by the efficiency of helical scanning. That 2-hour capacity changed consumer habits. It enabled the massive video rental store industry and gave ordinary people the ability to record live television as it aired, saving it on a shelf to watch later. This technical advantage, efficient data density resulting in longer continuous playtimes, was the primary weapon that allowed VHS to defeat Sony's Betamax in the famous format wars. The engineering logic of a tilted drum wasn't just a solution to a math problem. By making a feature-length tape small and affordable, JVC built the foundation for the mass-market home movie industry. Of course, the analog nature of the format demanded a toll. The high-speed physical friction between the head drum and the plastic ribbon meant that every time you rewound and watched your favorite movie, you were slowly scraping away its magnetic memory. As a viewer, you simply sat back and watched a story unfold on the glass. But behind the plastic casing, a violent, high-speed physical interaction executed with precision to keep that story alive. Today, our movies have become weightless files on a server, but for decades, bringing cinema into the living room required this specific combination of spinning metal and magnetic tape, a piece of complex, tangible engineering you could hold in your hands.